Section 2.5, Solving Compound Inequalities. Part 1 of this section is going to be looking at what we call OR problems. Let's frame this in a way that maybe makes a little bit more sense outside of algebra. We're going to start. Mr. Calnan here is hosting a party, and you are invited if you've ever been named Super Bowl MVP or if your name is Tom. So you see we have a little Venn diagram down below. So you got some Super Bowl MVPs who are invited. So we've got a few there. Let's see who else is invited, or who is invited first. So we get Troy Aikman, who had won the Super Bowl MVP with the Cowboys. Dexter Jackson, defensive back from the Tampa Bay Buccaneers, won the Super Bowl against the Raiders. And we get Patriots wide receiver Deion Branch, caught at the time a record number of passes against the Eagles to win the Super Bowl. Now there are certainly others invited as well, but those are some examples of three guys who are invited because they won Super Bowl MVP, not because their name was Tom. But you know, that's another option. You could be invited if your name is Tom as well. So who would be invited there? Let's see. First, we've got Academy Award-winning actor, star of the upcoming Bridge of Spies, Tom Hanks. Sticking with Hollywood, we have Tom Cruise. Tom Cruise is invited to Mr. Callan's party. And let's see, other Toms. Well, what do you know? Algonquin's very own Mr. Tom Meade, our principal, is also invited, being named Tom. And, of course, there's somebody else that we haven't mentioned here, one of the most important figures in either category. And that would, of course, be the quarterback of the New England Patriots, Tom Brady, who's invited. And not only has he been named Super Bowl MVP multiple times, but he's also named Tom. So that's why he's in the middle of this Venn diagram here. And so what you see, and this is, you know, kind of a similar problem to what we looked at in class with the stand-if activity. What we have is we have people who are invited because they were Super Bowl MVPs, people who are invited because they were named Tom, and then we have people who are invited for both reasons. All of these people would be invited to the party. Who's not invited to the party? LeBron James. That's who. And look, he's very upset about it because it's going to be a good time. But LeBron James has never been named Super Bowl MVP, and he's not named Tom. So since he doesn't satisfy either condition, he can't come to the party. That's the point of an OR problem. The OR in here tells me that one of these two things has to be true. Being named Super Bowl MVP or being named Tom. If either of those is true, you can come to the party. It's okay if both of them are true. Then you're also welcome. But if neither of them are true, you have to sit out and be sad like Mr. James. All right, now let's bring this to some algebra. In order to look at this algebraically, we're going to be looking at what we call combined inequalities. Inequalities that are combined by the word or, just two or more inequalities that are done at the same time. With or, they're also called unions or disjunctions. Just some vocabulary there. And occasionally we'll use this symbol instead of the word or. So let's take a look at a problem here. We have 3x plus 6 is greater than 8, or 6 minus x is greater than or equal to 10. All we're going to do is we're going to solve each inequality separately. So go ahead, take a second, solve each inequality, come back and check your work. All right, how did it go? And there we are. You can see that we just solve each inequality. On the right one, I had to flip the inequality sign from a greater than to a less than because I divided each side by a -1. And I get x is greater than 2/3 or x is less than or equal to -4. Now what I'm going to do is I'm going to graph each solution. I've got two different solutions here on the same number line. So I'm going to do that. And that's going to be a closed circle at -4 going over to the left for the x is less than or equal to -4, and an open circle at 2/3 in between 0 and 1 going off to the right for x is greater than 2/3. Now that I've graphed each solution, I want to finalize the answer by looking for the part of the graph that is covered by at least one arrow. So on this number line, there are pretty much three areas I'd want to look at. I want to look at this area, which is on the left of -4. I want to look in between -4 and 2/3. And I want to look at this area, which is to the right of 2/3. Where is there at least one arrow? There's at least one arrow here and at least one arrow here. There's none in the middle. These numbers in the middle will not satisfy either of our original inequalities. The numbers on the right, 1, 2, 10, and so on, will satisfy this inequality. The numbers on the left, -5, -10, etc., will satisfy this inequality. As long as I've satisfied one or the other, it's good. But I have to satisfy at least one for it to count. Therefore, my solutions are over here and over here. This graph, where the arrows point away from each other, is the most typical OR graph that you're going to see. And so that's something that you should look for when you're solving these problems. It's not going to happen all the time, but when it does, there's a pretty good chance that we've done it correctly. All right, let's take a look at some other examples. All right, so let's take a look. Sometimes the graphs can be a little tricky. So what we're going to do is we're going to start by solving each of these two inequalities in this combined inequality here. So take a second and do that, and then come back and check your work. You don't need to worry about graphing yet. All right, let's see how it went. So when you solve this over here, you should end up with x is less than -4 or x is less than 2. Let's graph each of those on the same number line and see what happens. So this looks a little bit different than our last example because both arrows are facing the same direction. Now we didn't actually do anything wrong. All that we have to do is we have to think about what it is exactly that OR means. To do that, we continue to look for the section covered by at least one arrow. The -4 and 2 are kind of like breaks in our number line. So the section to the left of -4, the section between -4 and 2, and the section to the right of 2 are all things to be considered. To the right of 2, I have no arrows at all. So my numbers over here are not solutions to my inequality. In the middle, between -4 and 2, I have an arrow covering it. So that means that the numbers inside there are solutions to at least one, or solutions to one of my inequalities, and therefore satisfy the condition of OR. The numbers to the left here, to the left of -4, numbers like -5, -20, etc., actually have two arrows. That means that they'd satisfy both inequalities. That's okay. We're allowed to satisfy both if the word is OR. So what we'd want to do is we'd want to finalize this by only selecting the part of the number line that is covered by at least one arrow. And that would be everything not only to the left of -4, but also between -4 and 2. So all we have to include is this part. Drawing this arrow is redundant. It's excessive and we don't need it. So we want to leave our answer just as this. That's actually what ends up being our simplified answer. All right, let's try the next one. Do it the same way, solve it, and then we'll come back and graph it after that. All right, how did it go? So what we see here is that when we solve these inequalities, we get x is greater than 0, or x is less than 5. So let's put those on a number line, the same number line. And here we are. What we can see is that we actually have these arrows going in the same direction, or opposite directions, but they come towards each other, as opposed to what we see as a typical OR where the arrows go away from each other. So, because this is the case, we have to still consider exactly where the sections are that are covered by at least one arrow. Using the 0 and 5 as our breaks in the number line, we have at least one arrow over here. The numbers to the left of 0 satisfy this inequality. The numbers between 0 and 5 satisfy both. And the numbers to the right of 5 would satisfy this inequality. So as a matter of fact, everything works here. Absolutely everything. So let's take that and say, what do we do when everything works? Well, we know what to call it. We call it all real numbers. And so that's how we describe our solution set. Now, if we really wanted a graph, we could have a number line. We could put nothing on it. We could put 0 on it. And then the graph would just be another line directly above it if you were really insistent on providing a graph. But all real numbers would be sufficient. Or you could use the all real numbers symbol. That would also work there. So, a couple of special cases there, but again, just look for where the sections are that are covered by at least one arrow above the number line, and those will be the answers that you want. All right, time for you to practice. All right, so we're going to go one at a time here. You can solve these and then graph your solution set. So go ahead and do that, and then come back and check your work. I'm going to go all the way through with including the graphing here too. All right, how'd you do? So this first example is pretty straightforward. It's a typical problem where the arrows will end up going away from each other and forming that shape of the graph. You get x is greater than or equal to 5, or x is less than -5. All right, same thing with the next one. You see here we've actually used that U to indicate that it's a union, that it's an OR problem. So just to familiarize yourself with that. And go ahead, try to solve these two inequalities and graph the solution set. How did it go? All right, this one here is just a little bit different. When we solve it, we get x is greater than or equal to -1, or x is less than or equal to 6. When we graph that there, we see that we actually have something that looks different than a typical OR, and there's at least one arrow everywhere. There's one here, two here, and one here. So when that's the case, we know we're dealing with all real numbers, so you can get a number line that covers everything. All right, how about two more examples? Alrighty, so let's take a look at these here. We'll do the first one first, solve it, and graph it. How did it go? Alright, so we can see here, after distributing our negative and solving each inequality, we get x is less than 5/4, or 1.25, 1 1/4, any format would be fine. Or x is less than or equal to -2. And with either of those, we do the graph, and we notice that they're actually heading in the same direction, so it's not typical, but that's okay. And because we just need to satisfy at least one of them, all we need to really draw is the one from 5/4 to the left, because that will cover everything that's covered by the other one as well. All right, one last example. Go ahead, solve it and graph it. How'd you do? All right, so this one's actually just slightly different as well. When we solve the first inequality, we get 3 is greater than or equal to 2, which is a true statement. We know that when we solve an inequality and we get something that's true, that means that the solution set for that inequality will be all real numbers. Solving the other one, we get x is less than or equal to 9. The graph of all real numbers, as we said, is just that one line that goes all the way across the number line. And then we have less than or equal to 9, closed circle going left. And we just have to satisfy one of these. Well, because the all real numbers is satisfied for every number is going to satisfy the inequality as a combined inequality. A number to the left of 9 will make both of these statements true. A number to the right of 9 will make only this one true, but that's all that I need. So if you're solving an OR inequality and you get all real numbers as one of your solutions, you almost could stop there, because it doesn't matter what this is. If everything is counted in here and I only need to count it once, that's good enough. So there you go. There's some good practice. Hopefully this makes a lot of sense to you.